Hi, I'm Everett Markwalter, and this is my Lab 5 lab report. So first, an introduction. The purpose of this lab was just to explore Faraday's law, and we're going to do that by modeling and experimenting with a bar magnet being dropped through a tube of aluminum foil. The model we're going to model the tube as a series of rings. Principles, we're going to use Faraday's law, the Biot-Savart law, Ohm's law, and Newton's first and second laws. And then a sneak peek of my findings, I measured the fall time on average to be about 1.151 seconds. The calculated theoretical fall time was 0.973 seconds, and the calculated dipole moment based on that theoretical calculated fall time was 2.704. So here's our equations that we're going to be using. Here's our concepts. We're going to have the Biot-Savart law magnetic field formula, which we use to calculate the magnetic field of the bar magnet at off-axis positions. We've got the concept of magnetic flux here, which the area here that we're going to be integrating over is like the area of like the cross-sectional area of the tube. We have Faraday's law here, which shows we have a changing magnetic flux because the bar magnet is moving, which will create a induced voltage in a loop of conductive material, and specifically we have the formula for it down here. This is from one of the videos. Then we have Ohm's law, which gives us the current based on that voltage, and the resistance here is based on like resistivity and all that. The code does that, like the base code that we're given does that for us. So we just need the resistance, so the voltage over that resistance gives us the current. Magnetic force is based on that current, and then the force of the magnet on the wire is going to be equal to the force of the wire on the magnet because of Newton's laws, and also forces mass times acceleration because of Newton's laws. So the experimental procedure. First, we're going to designate the north pole of the magnet. We're going to figure out which side that is. We'll weigh the magnet, record its mass. We're going to measure and record the dimensions of the aluminum tube. We're going to need that for our code later. It's the length, the inner diameter, the width of the aluminum, all that. We're going to drop the magnet through the tube multiple times and videotape it, and use that video to figure out the time it takes to go from the start of the tube to the end of it. And then we're going to model that experiment in GlowScript Python using the dipole moment that we found out from Lab 3, and we're going to compare the results. So the assumption of the system is a tube of aluminum foil and a magnet on Earth. Surroundings are the rest of the room the experiment was done in, so any electronics could mess with the experiment. The magnetic field of the Earth could mess with the experiment, and gravity is going to be 9.1 about here in Georgia Tech. So the assumptions we're going to use: air resistance is negligible, the size of the magnet is negligible, magnetic fields from anything other than the bar magnet in the tube are negligible, the tube is perfectly cylindrical, and we're going to model the tube as a bunch of rings stacked on top of each other. And these are the assumptions just for the coding model. So what results for the experiment: we get an average time to go through the tube of about 1.151 seconds. And then here are our measurements. We're going to use those in the code. Here they are in the code on the left. And on the right, I have my functions that give us the magnetic field from the Biot-Savart law formula and the deflux dt from Faraday's law. And then what the code does is it updates the magnet's position and velocity every point, like 1 second, and it loops through that until the magnet leaves it. So it like updates the magnetic field, all the flux, all the currents, all that every 0.001 seconds, and it loops through that until the magnet leaves the thing, and then it gives us the time. So the calculated time from that is 0.937. The actual time was 1.151. And then I noticed that the magnetic dipole moment varies with the square of the time. So we take the square root of the time and multiply by the initial, like the dipole moment that we use for the experiment, and we get calculated mu is 2.704. So what if questions? If the resistivity was reduced as close as possible to 0, this R would increase super high, so the current would decrease super low, so there would be basically no force on the magnet, so it would just fall like normal. And then what if the holes or slots were cut into the tube? How would this affect the ring currents? So Faraday's law doesn't actually need to be a physical loop. It can be like a drawn loop, so it wouldn't actually affect the ring currents other than like from this resistance formula here, like the L would decrease.